In this video, we're going to be demonstrating how we can calculate the chi-squared values and run these chi-squared tests in R. And we're going to be doing this in a few different ways with a few different data structures. So a big part of this presentation is going to be talking about how we clean those data structures and get them into the format that R needs to run this analysis. And because we will have a bit more time today, because the analysis isn't super complicated, and even with the cleaning or the reformatting, it's not going to be too complicated. We'll also talk a little bit about cleaning and introduce a data set that's so big that it can't fit into Excel, so that you can say you've worked with data that size before. So for me, when I start a project, I typically read in all of my data as the first step. So I don't read it in one at a time, I just read it in all at the beginning. Incidentally, I also put in all the libraries at the beginning, but you kind of have to know what libraries you're going to be using as in the project to be able to do that. So we won't do that here. Sometimes it is nice to be able to put the data steps in each place. But as a habit, I try to put it all at the beginning so that I can really quickly see what data I have to have access to. Now, you can't see it on this screen, but in my folder that I have for this, I have a subfolder called Data, where I store all of my data. I don't just keep it in the same folder as all my R scripts. So when I open up a script in R, if I have this subfolder in the same location called whatever, mine's called data with a capital D, yours can be called whatever you want, data sets or Excel files or CSV files or whatever you want to call it, then you can access the data files without changing anything and without typing in the full path name, just by telling it, hey, it's in this subfolder, and look in there for the data set. So we're going to look up the chi-squared data structure 1. .csv. Now when I read in all my data the first time, I read it in and I make sure that it displays nicely. Okay, that one worked, so now I'm going to go on and copy and paste, and I've got 5, 1, 2, 3, 4, 5, and data structure 2, 3, 4, 5. Now it saves a lot of time to do this copy and paste, but you have to make sure that you remember to change both the file name out here and the data name, because if you miss one, that's going to throw you for a loop later on. And I'll go on, Control A, highlight all those, and then read all of those data in. This last one, DAT5, is the one that's so big that it doesn't fit into Excel, and you see that, at least on my computer, it loads in R in less than a second. So it's very, very, very quick, very, very efficient. So we already looked at data 1, and we can see that in this case, this is kind of like our traditional demonstration of how this should look. It's our very first table format. In fact, all of our data are going to be the same one. I didn't do every problem in the notes, and the reason is because I wanted to demonstrate how the same data can look in a whole bunch of different ways. So that's why we're doing it that way. But looking at this, the weird thing is that the yes and no aren't the row names. They're actually their own column that has its name called X. So that's kind of weird, and run two are the row names. So we'll need to change that up real quick. So I'll make a section title working with DAT1, and I make it a section title by starting a comment and then adding 4 horizontal tick marks or hashtags at the end, and that makes it a section title. And then I will say that the row names for DAT1 should be the first column of DAT1. So remember these brackets, go row, comma, column, and if I don't list a row, it says all of the rows. So this is a way of saying I want the first column and all of the rows from DAT1, and those are going to be the row names. And if I look real quick at DAT1, I can see that now I have the row names, but then it's also repeated. So I've changed the row names from 1 and 2 to be yes and no, but now the X, that list of row names as a column, looks a little funky, so I want to get rid of that. There's a couple of ways we can get rid of that, but one of the easy ones is the subset command. This is a way to take a subset of your columns. So I tell it what data set I want to do, and I tell it what columns I want to select. Now in this case, I don't want to select a column, I want to deselect a column. So I'm going to write minus and then capital X. That's the name of this column, not lowercase x, but capital X. Incidentally, if I did a minus lowercase x, it's going to tell me, hey, you don't have a lowercase x name, and I'd have to look at that and really squint, and I see, okay, maybe that's a capital X. In any case, I can look at dat1 and I see that this looks appropriate. This is exactly what I would expect my data to look like and matches what the data looked like in our notes. Incidentally, this data format, it's called a table. Sometimes you'll hear it called a crosstabs or a contingency table. This table is the format that we like to use for analyzing the data in Excel. So running a chi-squared. Once we have the data in this format, running a chi-squared, I use the command chi-sq.test. And then I run it on my data. And it comes up with the chi-squared statistic, the degrees of freedom, and the p-value. Very cool. It's very straightforward, and the output is relatively simple when compared to some of the other ones we've been looking at. Now, if you save this, I'll call it dat1 mod, and I'll just save the chi-squared. I can always go back and look at it after it's been saved. So if I type dat1 mod, I can always go back and look at that. Oops, I'm getting an error here. My Google Drive's not letting me sync. I apologize. But dat1 mod lets me always go back and look at that information, which is very cool and handy. But it also gives me some more information. So if I do dat1 mod and then a $sign, I can pull specific pieces off of this. So one of the things that I can look at, as we discussed, the observed values, and that's just the data that I had in, but we compared them to expected values, and we discussed how we calculate the expected values. Well, calculating the expected values can be a little bit of a pain, but if I run the commands this way in R actually gives me, as part of this chi-squared test, the expected values if I save it as a variable and then ask for the expected values specifically from it. So I can go on and calculate that pretty easily. It's really nice and handy. One other thing that I can calculate using this is the residuals. So this is kind of a standardized, it's very similar to like a t value or a z value score of how far these are off. So we discussed how we can look at where the differences are utilizing a comparison between the expected and the observed, like where we just squint our eyeballs and say, oh, 97 is really close to 97.5. But this standardizes it on a z-scale where we can say, okay, if it's bigger than 2, that's pretty big. If it's close to 2, like this one's relatively big. In the negative direction, this one's relatively big. In the positive direction, then anything above 3 would be ginormously big. So these can be pretty helpful when you're trying to figure out where the differences are in the groups. And again, negative sign means that this is less. So we have less, no, I wouldn't get it again, log houses than we would expect by chance. And more, no, I wouldn't get it again, A-frame houses than we expect by chance. So I interpret this as A-frames are a little bit worse, A-frames are a little bit worse, yes, and log houses are a little bit better. All right, well, let's move on to the second data format, working with dat2. We'll come back and do the post hoc tests a little bit later after we're done, but let's look at our data. So I'm going to hit Control and L on the right-hand side to clear the screen so that I can work on dat2 specifically. And here we see we have the long format that we also saw in our notes. But this long format is not formatted in the way that R needs it to be formatted. So what I need to do is reformat the data. So I'm going to call it ref dat2 to stand for reformatted dat2. And I'm going to use the command X tabs to reformat this particular type of data where I have only one listing of the group. So there's only one place in the whole data set where repurchase says yes, and the type of home is a colonial home, and it gives me the frequency, how many times this particular group of variables. That is, yes, colonial. How many times did that happen? It happened 97. So when the data is formatted in this way, it's kind of a unique formatting. I use this kind of unique command. And to be quite honest with you, I had to look this up because I haven't used this command in a while. Because it only, for me, I only use it when I have data that's of this particular format. So I'll put the count as the thing on the left of the squiggle, and then on the right of the squiggle, I'll have my two categorical variables, repurchase and homeowner is what I called them. You would put in whatever you called them, and then tell it what data set I'm using DAT2. And if I look at this reformatted data, I can see that I now have the same format, not necessarily the same order, but the same format as DAT1. And you'll notice that if I compare, it's not the order that's important. What's important is that the right number is at the right spot. So for a yes, I would get it again colonial. There were 97 people who said that. Here, yes, I would get it again colonial. There are 97 people who said that. So that is the important thing. Let me say it one more time. The order of the numbers, 97, 83, 80, that doesn't matter. What matters is that when I read this, how many people said, yes, I'd get it again log house, that I get the same number no matter which table I use. 83 people said, yes, I'd get it again log house. 83 people said, yes, I'd get it again log house. That is the important thing here. So because that is working, then my data is properly formatted. Now I can go on and run my chi-squared test with my reformatted DAT2, not my regular DAT2. Notice if I just put DAT2 into here, not the reformatted DAT2, it's going to give me an error. It's going to say I don't know what to do with all these character vectors, and that's fair because again, R is expecting you to give it a grouping of numbers with labels around it. So in this particular case, when I give it the proper formatted data, I get the exact same result as I got previously. All right, we're cruising. So now we're going to talk about working with DAT format 3, and I honestly don't remember how this one's different, so let's investigate. For me, after I'm done with a particular section, I tend to do some spacing, like 3 empty lines or 5 empty lines between the sections so I can keep it neat and then kind of group all the commands within with maybe 1 empty line, but no more. Same thing over here. When I move to a new section, I tend to clear off my screen so that it's nice and fresh for the new data set that I'm working with. Oh my goodness. Okay, so in this one, this is what if you went out and asked one person what would they get their repurchase their home, this is what the data would look like. Here's the first person. They said no, they wouldn't get it, and they had an A-frame home. Here's the second person. They said yes, they would get it, and they had a log home. Here's the third person. They said no, they wouldn't get it. They had a colonial home, and so on and so forth. So this is what raw data very well could look like if you actually asked this on like a survey of homeowners in a community. So where do we even start? Well, first of all, if I just look at a large data set like this, it can be a little overwhelming. Now, this is only a few hundred rows, but even still, this is kind of overwhelming. R has the head command that just pulls the top few observations of the data so that I can see what it looks like. And this looks less overwhelming. In fact, I'm going to clear my screen because that's just a little too overwhelming and just use this head command to remind myself of what this data looks like and how it's entered in. Now, just like we used this xtabs command previously, the command that we'll use with this format of data is the table command. So if I do table dat3, $, and then repurchase, this is going to ask how many people answered repurchase yes and repurchase no. And similarly, if I do table dat $, homeowner, this is going to ask what type of homeowner are individuals, A-frame, colonial, log. And I can see there's 101 individuals in my survey that owned a log home. Now, what I really like about this is that it gives this very, very nice, convenient, quick overview of a categorical variable. Unlike xtabs, which I don't use particularly frequently, I use table in virtually every data set I analyze. This function, this exact function right here, is just so darn handy to be able to use that I end up using it in virtually every data set. Now, the nice thing that we can do with this is that we can actually do both of these categories together. So if I do table and then I give it DAT3 for repurchase, and then DAT3 for homeowner. Nope, I'm getting an error. What does it say? DAT is not found. Well, I didn't try to use DAT. Oh, there it is. I did a typo. Should have said DAT3. Okay, then I get this nice table that looks very similar to what I had for DAT1 and the reformatted DAT2. So hopefully all of these three are looking very similar. And again, the order is not important. What's important is that the numbers are the same if I look at one. So let's look at no. How many people would say, no, I wouldn't get it again and had an A-frame? Well, here's the A-frame, here's the no, 44, 44. Okay, perfect. That looks like it's lining up correctly. I might spot check a few numbers. Quickly, I see that R's format is alphabetical. So A-frame colonial log is how both the reformatted data and this table is organized. And then no, yes instead of yes, no. The only reason it's doing this is because it does it in alphabetical order. You certainly can change that if you want to. We won't talk about it here. So because this table format is the format in which I want my data, I'll call it tab dat3 and then save this table as a data set, tab dat3, that I can use for my analysis. And now, with the properly formatted data, I'll go on and do the chi-squared analysis, tab dat3. And we see that I got the exact same results as previously. Again, once the data are properly formatted, then I can run the analysis, and it didn't matter what the original format was, as long as the information's the same. The results are going to be the same. All right, working with DAT4. And now we're going to talk a little bit about data cleaning. So now I know that I don't just want to type in DAT4 because that's going to give me a whole ton of observations, that I want to look at this using the head command first to make sure I'm dealing with this slowly and not overwhelming myself. Now I'm going to do table DAT4 and look at the repurchase and homeowners, and I do this every time when I break this down. And actually I see that here there's a couple of different things going on. I'll start with the repurchase. I see that there's a lowercase yes and an uppercase yes. There's only one. It looks like it was a typo. That's a lowercase yes. So I'm going to have to deal with that. Same thing with A-frame. I'm going to have to deal with what looks to be a typo because R is treating it as a different category. And to be fairness, it is a different string if you care about capitalization, and R does. So it's a different category right now, but that's not intentional. It looks like a typo to me. Now in R, I'm going to deal with repurchase first. I can quickly ask which one of these is that. So I'm going to use the which command to ask which one of these is that lowercase yes. And I'm talking about DAT4's repurchase column. And I want to know which one of these repurchased answers is a lowercase yes. Now I use two equal signs to ask the question which one of them is equal to. So to ask the question, is it equal? Then I use the double case equal signs. I use an equal sign in place of the arrow. So that would say dat repurchase should be reassigned to be the string yes versus asking a question, is it yes? In this case, I see that the 26th observation is this lowercase yes, and that's interesting. So I really quick want to look at the 26th observation. So row 26, I'll look at both columns. I could just look at the first column if I wanted to by putting in a 1 after the comma, but I'm not going to. I'll look at both of them. And I see, yep, there's a lowercase y yes there. So I need to fix that. And there's a couple ways I can fix that. I can go into the original data and fix that. But sometimes it's more convenient to just fix it in R. So I'm talking about the 26th row and the first column. So now I'm going to get really specific about the exact value. And what I'm going to do here is I'm just going to change the value. So for the 26th row, that's this row, for the first column, that is this entry, instead of being a lowercase yes, this should be an uppercase yes. And now when I look at that row, I can see that instead of a lowercase yes, that has been changed to an uppercase yes. Don't forget, rows go first, commas go second. And if I rerun this table with repurchase, I see that now instead of having one lowercase yes, I have, and 259 uppercase yeses, I have 260 uppercase yeses. All right, let's look at this homeowner business. So in this homeowner, I have A frame as a lowercase a frame and capital A frame as an uppercase a frame. So I'm going to kind of do the exact same thing that I did earlier, except now I'm not talking about which DAT4 repurchases lowercase yes, I'll be doing lowercase a frame. And I'm not talking about the repurchase variable anymore. Now I'm talking about the homeowner variable, which dat homeowner is not lowercase yes, because that's going to be none of them, but is lowercase a dot frame. Oh, it still says none of them. Oh, because I misspelled this, a frame. There we go. And these are all of the ones that are this lowercase a frame. And if I counted these up, I should hopefully count that there are 20 observations that have this mistake made in the data. Now to go through and do this reassignment for each one of the 20 observations sounds a little bit tedious. So what I'm going to do instead is do the same structure, dat4, and now instead of talking about the first column, which was repurchase, I'm talking about the second column, which is homeowner. And the question is, what rows do I want to fix? I want to fix this second column to be a frame. Oh, and I want it to be the correct one, capital A, capital frame. So how do I get all these rows? I could just copy and paste this 20 times and type each of these rows into it. Or what you could do, this code from R spat out all of these row names. So instead of manually spitting out all the row names and then copying and pasting them back into R, I can just have R tell itself what rows to do. I'm going to copy this code that gave me all the appropriate row names and put it in the row names slot and run that. So now R is going to look at each one of these row names that R spat out to me up here and the second column for each of these, which is the homeowner column, and it's going to replace all of those which had a lowercase a dash frame to be an uppercase a dash frame. I can quickly check by rerunning my table, and I see that no longer do I have any lowercase a dash frames. They are all uppercase a dash frames. And now I can go on and run my analysis. So this is the data cleaning stuff where sometimes I have typos that I have to deal with. And this happens all the time, especially if somebody's hand entering a data set. It happens all the time that I'm dealing with typos in the data that I need to go fix. So this is a very common occurrence. But once that's dealt with, the commands to create the information I need is pretty straightforward. I just follow the same process as table 3. Where I create the table of it using the table command and then run the chi-squared analysis using the chi-squared test command, tab dat4. All right. And I get the same results as I had before. Fantastic. All right. Let's see, we're doing 5 lines. So 1, 2, 3, 4, 5 empty lines. So now we'll try working with dat5. So DAT5 is the big data set. This is the one that doesn't fit into Excel. So if you want to see how big does a data set have to be, well, first of all, let's look at DAT5. And you don't just want to type DAT5 because, again, it's got a lot of observations. Looks like the first 3 are A-frames, the second 3 are colonials, and it's just got a whole bunch of different observations in there. How many observations? Well, if I do dim dat5, this asks for the dimensions, the number of rows and the number of columns in this matrix. Well, it's only got 2 columns, but it's got 1,048,577 rows. In fact, I made this to be one bigger than the number of rows Excel can handle. So Excel can handle 1,048,576 rows. This has 577. So now you can say you dealt with a data set that doesn't fit in Excel. One trick here, though, is if you try to open it in Excel, it'll give you a warning, but it'll let you potentially open it. It might lag a lot. The problem is if you save that, it will delete all of the observations that you didn't have loaded in the data set. So if this was 2 million observations and I opened it in Excel and then saved the file, it would delete half of my data just from opening in Excel and saving. So you want to be really, really careful with that. Real quick, I'm just going to copy the same table that I've been making. I would, if I were being good, go on and double check. I'm going to change to be DAT5 instead of DAT4. This will show me if I had like a misspelled A frame or a misspelled yes in this table. And then I would go and do the individual tables to get some more information, and this same process, even with a large data set. Again, you can see this distribution. It's really funny just how big these numbers are, 175,000, 174,000. And this highlights an interesting thing about large numbers. If these are all supposed to be equally likely, man, these ones are 200 off from one another. That sounds like a huge number, but on the context of 175,000, maybe being 200 off isn't that large given how big the numbers are. And when you start thinking about that, you kind of shrug your shoulders. Man, these are 300 off. Wow, so far. Or is it? I don't know. This is where the statistics can be really helpful. Like the scale, the measurement of the numbers don't really mean anything. It's difficult to comprehend. So this is where our statistical analysis can be very, very, very handy. So I'm going to go on and save this table as tab DAT5 and then run our chi-squared analysis on this. Chi-squared test tab DAT5. And I could save this. I could look at the residuals. Actually, maybe I will. I'll do mod DAT5 for the model, and then I will look at mod DAT5 and look at the residuals, $resid, and see, okay, well, first of all, this wasn't statistically significant, so that's good. I see that, man, these are 300 different, but that's not different enough to be statistically significant on this scale. And again, how would you know? Well, there's not necessarily a good way to know intuitively. These are just immense numbers, so I would need to use statistics to help me determine that. Incidentally, sometimes how it turns out is these are very, very, these turn out to be statistically significantly different, but the size of the difference is pretty small relative to how many there are. So a lot of things can go on with big data that you want to be a little bit careful about, but at least in this case, the stats are helping us quite a bit to say, no, there's actually no difference between these that's statistically significant. That is, there's no preference between A-frame, colonial, and log houses in terms of the number of people who would repurchase them or not. So this is a different data set than we had before in that we're getting a different conclusion there. All right, so the last thing that we have to talk about is the follow-up testing. So if I'm running follow-up testing, one thing that I might use is the total. So I'm actually going to work with just DAT1, just this data set that's already nice and neatly put together. This is kind of the original data we had from our notes. Now for follow-up testing, I need the number of successes and the number total. So I have to calculate this. Real quick, I can apply the number total for each column using the apply command. So I'll do DAT1, and then I have to pick margin, all in caps. I can do 1 or 2. 1 stands for row, so I can sum across the rows. That would be the total number of yeses, the total number of no's. In this case, I want to sum across the columns to do 2, margin equals 2. So the total number of colonial, log, and A-frame homes. And then I give it the function that I want it to do, the mean, or in this case, I want to do the sum. All right, so that's how I do the total, and I'll go on and save this as a command called, or as a variable called tote. And then the number of successes. Well, I'll want to see the number of yeses and no's in this particular case. So I'll want to see how often is let's see, the number of successes. So this is just the yes column, actually. I already have this all calculated. I don't have to recalculate anything. This is just the, or excuse me, not the yes column, but the yes row. So how I can ask for the yes row is I can just put the first row in the command there, or I can give it the row name. Yes, either way works well. Now for the follow-up comparisons for success, normally this is all I would have to do is just say I want the yes row where I could put the number 1 there. Unfortunately, this comes out as a data frame with 1 column, and we need it to be a numeric vector. So I have to add one more thing here. I have to do the asNumeric command to make this into a numeric vector. And now if I look at this variable, you'll see it's slightly different than this data frame with just 1 row that has a row names and column names. It comes out as just a bunch of numbers for the successes, and that's what we need for this command. All right, now it's funny because I still want the names to be around. So the names of this, the numbers are going to be helpful in the command. So I'll do the names of this vector are going to be the column names from my data. And now if I look at the successes, I still have the names. Again, this is going to be helpful for the output. This line right here where I change the names is not necessary for calculating the correct output. It just helps me interpret it a little bit. All right, so the pairwise test is going to be the command pairwise.prop.test, and then I give it the number of successes and the number total. Actually, we already used this command previously, but in this case we can see pairwise.prop.test with the number of successes and the number total. I get a comparison of these different values, and actually each of these are the p-values for these comparisons. So I see that Colonial versus Log House is not statistically significant. Colonial versus A-frame is not statistically significant. These are p-values. They're greater than 0.05. But this A-frame versus Log House is statistically significant at the p equals 0.05 level. So in A-frame versus Log House, I see a statistically significant difference. Interpreting this, I would just say A-frame is different than Log House, and it's neither of the houses are different from Colonial. Colonial's not statistically significantly different from anything. We looked at the proportions previously in the slides, and we saw that Colonial was kind of in the middle of the proportion of people who liked A-frame and the proportion of people who liked Log, and that was why, because the middle one wasn't different enough, but when you looked at the very, very top and the very, very bottom, those were different enough. And that's how we got this. Now we're not using the LSD correction, that is no correction at all. In this case, R uses by default the Holm correction. And instead of talking about details, I'll just mention that this is a reasonable correction to use. You can just use R's defaults and that's just fine. If you wanted to investigate more, you can certainly use the method argument. That is, you type in comma method equals and you could put in Bonferroni or something else. I don't believe it has the method by name that we used in the book. I think that method would be considered none by our standards. In fact, I'll just go on and run that real quick. Hitting the up arrow, I can quickly gather the what I was using earlier, and then method equals none. Oh, and it's not letting me use method equals none. To get more information, I can do question mark, and then this test, it's called p-adjust method. So that's what I need to use here. So I'll use p.adjust.method, and that, nope, and I need to take out the question mark. Up arrow gets me the previous line. Delete the question mark. Okay, perfect. And then I get the p-values of each of these comparisons with no adjustment to the p-value. Again, this is what we did in our textbook, how we would implement it into R. But the R's default settings tend to be pretty good. So I guess it depends on the command. But in this case, this is default is probably better than what we talked about in our notes to use for this comparison. So this has been a demonstration of how we can do the chi-squared test in R, working with some different formats of data that we can get, working with a data set that's so big it can't even fit in Excel, and then discussing the follow-up tests with how we calculate the number of successes and number of totals from a given table, and how we can do the pairwise proportional testing using the pairwise prop test command in R, and change our p-value adjustment methods from our default to a worse one so that we can match our notes if we want, though we would recommend that you stick with the default or use something that you have a bit more theoretical support for. In the next video, we'll get going on our next chapter. So this ends our chi-squared chapter.